Okay, so before the short break just now, we have already looked into the overview of a turbofan and then a milestone of turbofan engine, classifications of turbofan engine, and we look into the category of forward fan unmixed double spool configuration, right? So now we want to look into the another type of forward fan, but this time around it is a mixed flow engine. The forward fan mixed flow engine, normally mixed turbofan engines are always found in either single or two spool engine. So it was used in the past for military applications only. Nowadays it is used in many civil aircraft, but nearly all military aircraft. Example of two spool engine in civil aircraft is the CFM 56 series. Alright, so over here is a snapshot of the CFM 56 evolution path. As we can see in this particular case, the CFM 56-2 engine was used initially in the military aircraft, also being used in DC-8, right? And produces 22 to 24,000 pound of thrust. Okay, it is a base specific fuel consumption SFC in 1979. Okay, and then it is being evolved into the 60-inch fan. Okay, in 1984, where CFM 56-3, so being used in the Boeing 737-300 aircraft, 737-400, as well as 500. As you can see, the amount of thrust being produced is about the same, but the range is slightly different, having advanced fan aero. So, and then next it is from 60-inch, it goes into the 68-inch fan. Right, this in 1987, right, being used in the Airbus A319, A320, having quite similar, but slightly higher amount of thrust being used, and it is a new aero throughout, and was used in FedEx 1. Okay. And going into the 72-inch fan, from 60 to 68, actually earlier is 56, 56-inch, going into 60-inch fan, 68-inch, getting larger, 72-inch fan blade, right? So you can see here in 1991, they got the certification for the engine being used by the famous A340 Airbus engine, right? It is a new fan, improved components, having mixed flow exhaust, having a higher thrust rate, 31.2 thousand to 34,000 pound of thrust. Okay, and the engine also being developed in such way, having the 56 CFM 56-5B. This is a 56-inch of fan, and then it is being developed in 1993 and 1996. This is new generation of CFM compared to the 1970s CFM engine, and at the same time they also come out with a 1996 CFM 56. Okay, CFM 56-7, 737-600, and the new 737-800 type of Boeing aircraft. Okay, being using this type of engine. Right. With regard to the forward fan mixed flow engine, and the cold compressed air which leaves the fan will not be directly exhausted, right? As previously described in the unmixed flow engine, but it flows in a long duct which surround the engine core and then mixes. And this is where it differentiates between the unmixed and the mixed, where this time when the air goes around the engine, it will mix back with the core of the engine. Okay, with will mix with the hot gases leaving the low pressure turbine. So thus the cold air is heated while the hot gases are cool, right? So meaning that you get a intermediate temperature of the mixed gases. Only one mixed exhaust is found in this particular type of turbofan engine. So most of the mixed turbofan engine now are two spool, right? If mixed turbofan engine are analyzed versus the unmixed turbofan engine, reasonable improvement in the following points are noticed. The first one is that the thrust generated, of course, it will be increased, further increased. You can have less noise, you have noise reduction, and you can provide reverse thrust, especially for braking purposes. Okay, hereafter a detailed analysis of this category will be given in this the following slide, and we will look into figure 6.15 and 16, which present the engine layout and temperature entropy diagram for mixed flow two-spool engine. So you can have the layout of a mixed two-spool turbofan. So you can clearly see here the cold air will be mixing back with the core of the engine, right? Where this is the hot gases going through the core of the engine, and it will meet at station number 8, right? It is mixing before only one type of hot or mixed flow coming out from number 9, station 9. And similarly here, for the TS diagram, you can see a different TS diagram. At different station, you have a different temperature and different entropy respectively. The requirements for mixing process are equal static pressures and also equal velocity, right? So thus, from the layout designation, these two conditions are specified as P prime 3, which is equal to P7, right? The pressure at P prime 3 equal to pressure at station 7, and the velocity prime 3 equal to velocity at station 7, and which means that if there is no pressure loss in our assumption in the bypass duct connecting the cold and hot streams, as well as no pressure loss in the mixing process, okay, you assume no pressure loss, okay? So the pressure at station 10 right after the fan is equal to this expression, right? Which is equal P10 equal to P prime 3, P7, and P8. If we quickly go there, okay, P10, P prime 3, P7, and P8, these are having the same pressure, right? There's no pressure loss from here till here, okay? So in real case, right, if losses exist, the fan bypass duct, so if there are losses somewhere there, there are air bleeds or whatever, so which resulted to the losses, pressure loss, okay? So the P prime 3 equal to the P10 minus the change in pressure at the fan duct, as well as the P7 will be equal to P8 and P prime 3. So in the above equation, we assume no pressure drop is considered during the mixing process. We assume over here, okay, there's no pressure drop. In some engine like the CFM 56 series, the mixing process takes place in a mixer preceding the nozzle. It results in a quieter engine, right? Of course, you want to reduce the noise than if the mixer was not present. Let us go into the process analysis. The first one is energy balance for the low pressure spool. Considering a mechanical efficiency for the low pressure spool zeta M1, then you can have the expression for the work over there, and you can also express it in terms of the mass flow rate as well as the temperature as well as the fuel air ratio and so on. 6.559. Okay, for the energy balance between before and after for the low pressure spool. And low pressure spool is what? Is the low pressure compressor which is connected to the low pressure turbine as well as the fan. For the high pressure spool, so you can also do the same energy balance for the high pressure spool. This time around you have the second mechanical efficiency, zeta M2. So you work out the expression where WHPC, high pressure compressor, equal to the efficiency of mechanical for the high pressure spool time lambda 2 time the work for the high pressure turbine. And then this is the expression for WHPC. This is the terms, and then this part, the remaining is the term. This on the right hand side term. And with regards to the mixing process, the hot gases leaving the low pressure turbine and the cool air leaving the fan bypass duct are mixed. Right, the hot gases from the core, it will mix the bypass air from the fan, and giving new properties at state number 8. Thus, such a process is governed by the first law of thermodynamics as follows. So you can have this expression that having at the state at number 8 itself, which can be reduced to equation 6.61. And for a better evaluation of the gas properties after mixing, we can use mass weighted average properties of the gas at state number 8. Right, so you can have the specific heat capacity at constant pressure at number 8, the gas constant at number 8, and the specific heat ratio at station 8 as well. Consider the real case of mixing where normally losses are encountered. Right, this is the real case compared to the ideal case, and we will have pressure drop, okay, associated with the mixing process. So such pressure losses are either given as the value of the delta P, right, the pressure at the mixing, or a ratio of Rm. This is the ratio for the mixing process. Okay, the Rm is less than 1, which is normally equal to 0.98. This is estimation, right? Next, you have to check whether the nozzle is choked or unchoked. For the case of the nozzle choking, if the nozzle is unchoked, the exhaust velocity can be calculated over here using this expression V9. And if the case of the nozzle is choked, you can have the expression as here, right? So thus, the thrust can be found using equation 662 for the case of the nozzle is choked. So, since more than 3 decades, most military aircraft are powered by low bypass ratio turbofan, which is fitted with an afterburner. One of the earliest afterburning turbofan is the Pratt & Whitney TF30 that powered F111, okay, and the F14A Tomcat. First flight of the TF30s, it was in the 1964. and production is being used until 1986. You can see that it's nearly span of 22 years. Afterburning gives a significant thrust, boost for takeoff, particularly for short runway like aircraft carriers. So that's why F-14A being used in the 80s in the aircraft carriers, or for transonic acceleration and combat maneuver. But of course, there is a penalty over there where it uses a lot of fuel. It is a fuel-intensive type of engine. So this engine is a mixed low bypass ratio forward fan 1. So the mixed flow still has a sufficient quantity of oxygen for another combustion process. So you can add on an afterburner. If you have an afterburner installed downstream of the low pressure turbine and upstream of the nozzle, you will have tremendous amount of fuel are burned in the afterburner when it is lit. And this rises the temperature of the exhaust gases by significant amount, which result in a higher exhaust velocity. In other words, you will have higher engine specific thrust. So for a turbofan engine, afterburning or reheat offers greater gains. Of course, you spend more fuel or of the relatively low temperature after mixing of the hot and cold stream and the large quantity of the excess air available for combustion. Exhaust nozzle is normally of the variable type to furnish a suitable media for different operating conditions. Unlike the main combustor, so the afterburner can operate at ideal maximum stoichiometric temperature. Normally it's around 2100 degrees Kelvin. But in the main combustion chamber, it is not this high, right? It's around 1300 or 1200 degrees Kelvin only, right? So now, at the fixed total applied fuel to air ratio, the total fuel flow for a given fan airflow will be the same regardless of the dry specific thrust of the engine. However, a high specific thrust turbofan will have a higher nozzle pressure ratio, resulting in a higher afterburning net thrust and therefore low afterburning specific fuel consumption, the SFC. It is interesting to add here that normally military engines are now so powerful that the latest fighter can supercruise, right? Flying at sustained supersonic speed. So it doesn't need to use afterburner at all. It can be cruising. We call it as a super cruise, right? Flying at supersonic at a very long duration. Example like Lockheed Martin, the F-22 Raptor, and the Eurofighter. Eurofighter Typhoon, for example, can accelerate to supersonic speed without using any afterburner or using augmentation. And then they can also sustain such a speed indefinitely in dry thrust. However, for the F-22 Raptor aircraft, it can supercruise at Mach 1.82 for a longer duration of time, while Eurofighter Typhoon can only supercruise at between 1.1 to 1.5 Mach number. So you can imagine that modern military engines are not using the afterburner facility because having an afterburner, it is much heavier compared to non-afterburner type of engine. Let us look into the analysis of a forward fan mixed afterburning low bypass turbofan engine. And the flow mixing will be the only difference in the cycle, okay, from that the afterburning turbojet. Okay, you can see that the only difference is the flow mixing. Okay, you can see in the following figures, we have 5 figures. Figure 617 will show the configuration of a single spool afterburning turbofan engine, followed by the TS diagram, and then a block diagram together with its input and output data. So following to that, a typical layout of a two-spool afterburning turbofan engine is displayed in figure 620, while its TS diagram for an ideal cycle is shown in 621 figure. Right. So this is a schematic diagram, a cutaway of a schematic diagram configuration of mixed turbofan with afterburner, right? So you can see it has the complex geometry intake, right? Not having any because this is to slow down the airflow that is going into the uh, fan stage. So you have a series of shock wave, normal and shock wave happening just to slow down the air speed before it goes to the fan area. And then going through 2 to 3 is the fan area, 3 to 4 is the compressor area, and 4 to 5 is the combustion chamber, 5 to 6 is the turbine, and we then have 7 to 8 is the mixer. Then we have afterburner from 8 to 9 before it goes to the convergent nozzle and convergent nozzle and then divergent nozzle. So before it goes back to the atmospheric at station number 10. So this is the associated TS diagram, right? It's much more complicated, right? For a single spool mixed turbofan with afterburner. And this is the block diagram for the single spool mixed afterburning turbofan engine, right? So you can see here the red arrows showing the mass flow rate, okay, going into the fan and then the compressor and then the combustion chamber, and this is a mass flow rate being added to the afterburner, okay. So and you can see all the connection for input and output from each component, starting from the inlet, going to the fan, going to the compressor, combustion chamber, the turbine, the mixer, afterburner, and goes back to the nozzle. So from here, the intake, the pressure will be the same at the nozzle. And for the fan, you can see that there's a work from the fan being connected to the turbine, low pressure turbine, right? And WC is connected to the turbine as well. And then from the fan is also goes to the duct before it go connected to the mixer. So it is this schematic diagram and block diagram is quite important to do the control system, right? To ensure that there is an input and output, how these components are connected to one another. This particular figure showing the layout of a typical two-spool mix afterburning engine. You can see here there's a afterburning segment at a station between 8 and 11, right? So it is a mixed turbofan, but this time around it has the afterburning component. So the numbering are already different. Now we have 12 section altogether. So this is the associated TS diagram, right, for the type of engine, mixed turbofan with afterburner. So the same conditions necessary for mixing described above still hold, and some of the approach will be the same as the mixed turbofan without afterburner. So thus the following relation stands for ideal condition where there are no pressure losses, the P10 equal to P7, P8 as well as P11. So you can try to refer back P10, P7, P8, P11. When there is no pressure loss, this area will have the same pressure. Okay. Normally, mixing process is associated with pressure losses. So in real case, there will be pressure losses, which may be governed by either one of the following equation for losses. You can have P08 equal to P07 minus the mixing pressure difference. Okay. And you can also have P08 equal to RM, P07, where RM in this case is less than 1. Normally it's around 0.98 value. Here, the P011 station, the pressure at P011 is the total pressure at the outlet of the afterburner. And once the afterburner is already operative. Okay. Moreover, the outlet temperature of the afterburner is T011, which is known in advance. Okay, because we know it's around 2100 degrees Kelvin, so that will be the value that the maximum temperature of the afterburner. It is limited by the maximum temperature that the material of the afterburner can withstand. So if the material is not so strong at the early stage, it is not reaching 2100 degrees Kelvin at all. However, it could be much higher than the total turbine inlet temperature. The turbine inlet temperature TIT, okay, if you see in this particular diagram, the turbine inlet temperature at station 5 over there, right, from the combustion chamber, will be less than the temperature at 11. So if you refer here, the temperature, you can see at station 5, right, compared to at station 11. So station 11, when the afterburner being turned on, the temperature is much higher compared to at station station 5. Okay, so why? Because this is the absence of mechanical stresses arising from centrifugal forces created by the rotation of the turbine blades. Now, using the mass balance approach in the afterburner gives the following afterburner fuel to air ratio, FAB. Okay, the FAB can be defined as 6.638 equation. Then using energy balance of the afterburner yields the relation of this 6.63 B, right? So this time around, you can see that there is a heating value, Q, the amount of heat produced by the combustion process in the afterburner. The pressure loss in the afterburner is also governed by the relation P09A afterburner equal to P08 minus delta PAB. Next, convergent divergent nozzle, right? So you go into the nozzle section, you converge and diverge, okay, will enhance a full expansion to the ambient pressure. So thus the jet speed will be given by this relation V12, right? So this will be your equation 664. If you want to look into the thrust force, now the thrust force equal to the mass flow rate of the exit time the velocity at station 12 before it goes to the atmospheric minus the m dot A coming into the engine and the V velocity of the aircraft. So with the exhaust mass flow rate is defined as m dot equal to this expression. You can also rearrange that. Then the thrust is now expressed in equation 665. Okay, so we move into the next part for turbofan engine. Normally turbofan engine require geared turbofan, or there's another case, it is ungeared turbofan. So geared turbofan are of two spool unmixed forward fan category. We have figure 622 and 623 that we are going to show afterwards. So since the fan is normally part of the low spool, both fan and low pressure turbine are turning at the same speed N1. This speed, however, often is a compromise. So the fan really operates more efficiently at low rotational speed, right? It is turn slow, much slower, okay, compared to the other component, especially the high pressure turbine and high pressure compressor, right? So the rest of the spool is more efficient at higher speed. So you have to find a balance because it is connected. Low pressure turbine, low pressure compressor, and the fan are connected through a shaft. So, but the fan will work more efficient at low rotation speed. So this is require uh, a gear system, complex gear system, to ensure that the fan is rotating at a lower revolution per minute compared to the low pressure turbine and the low pressure compressor and low pressure turbine. So you can see here, this is the fan blade and this is the planetary gearbox. We will look at the how does it look in the actual case. So 6.23 is a Lycoming ALF 502R geared turbofan. So there's a complex gear, planetary gear over here to control the rotation of the fan blade as well as the rotation of the low pressure turbine, low pressure compressor, and low pressure turbine, respectively. Putting a reduction gear in between the fan and the compressor will make it possible for the fan and the low spool to run at their optimal speed. Okay, namely N1 for the fan and N3 for the LPT. So this in turn will minimize the possibility of formation of shock wave in the fan, leading to a higher efficiency. The other advantages are more fuel efficient, reduced noise level, reduced emission such as CO2 and NOx, fewer engine parts, fewer compressor and turbine stages, as well as reduction in the overall operating cost. So this is the advantages of having the geared turbofan. The gearbox used here is of the planetary type. You can see why is it called as a planetary. It is you have one gear in the middle, so that it being connected by many other smaller gears that is connected back to the respective shaft. Planetary gearbox is a planetary gearbox is recommended as it is its length is short to match the minimum size requirement of a turbofan engine. Example of geared turbofan engine, low pressure spool may either compose of a fan driven by low pressure turbine or a fan and low pressure compressor representing the compression sections driven by a low pressure turbine. In either cases, a reduction gearbox is located directly downstream of the fan, which has already been shown in the schematic figure. Now, concerning thermodynamic analysis of a geared turbofan, if the mechanical efficiency of the gearbox is zeta GB gearbox, then the two cases can be examined. Firstly, the low pressure spool is composed of fan and low pressure turbine. The fan states at number 2 and number 3, and the LPT states are at 6 and 7. Okay, fan 2 to 3, low pressure turbine 6 and 7. We can write the energy balance for this relation. Equation 6.66, where B equal to mass flow rate of the bleed over mass flow rate of the air bleed ratio, defining the ratio between the air blade and the high pressure compressor to the core air flow rate, right? In the second case, the low pressure turbine state number 6 and 7 drive both the fan state number 2 and 10, as well as the low pressure compressor state 10 and state number 3. So then the energy balance can be expressed as 667. All right. Concerning the high pressure spool, with an air blade from a station just downstream the high pressure compressor and prior to the combustion chamber, so you can have this expression 668A. Next, if the air is bled from a station within the high pressure compressor identified by the pressure P03B, then the energy balance of the high pressure spool is given in this expression, right? So 668B. Okay, the last segment for turbofan is another example of forward fan unmixed three spool engine. Okay, we have already looked at double spool earlier before we have the short break earlier, and then now we want to look at the three spool. Okay, the three spool engine normally composed of a low pressure, intermediate pressure, and high pressure. So instead of having low pressure and high pressure, now we have the intermediate and the in between high and low, running at different speed, N1, N2, as well as N3. The fan and the low pressure turbine compose the low pressure spool. The intermediate spool composed of the intermediate pressure compressor and intermediate pressure turbine. The high pressure spool composed of high pressure compressor and high pressure turbine. So you can see that it is all connected, right? This one fan connected to the low pressure turbine, intermediate pressure compressor with intermediate pressure turbine, high pressure compressor connected to the high pressure turbine. Rolls-Royce was the first aero engine manufacturer to design, develop and produce the three-spool turbofan engine. And this is the famous RB211 type of engine, was the first three-spool engine to enter service in 1972. Right? So later on, other manufacturers developed and manufactured this type of engine to take advantage of the superiority of the connection arrangement. So this is a RB211 type of aircraft. This is RB211-524GH. You can see here the schematic diagram where the fan itself is connected to the low pressure turbine, okay, low pressure turbine, and then intermediate pressure compressor being connected to the high pressure compressor, and then intermediate compressor connected to the green one and green colored shaft connected to the intermediate pressure turbine, and high pressure compressor, it is connected in the red one, being connected to the high pressure turbine. Okay. The main advantages of having three spool arrangement, we have four advantages here. You can have a shorter module and shaft, which result in a shorter engine. Having single stage fan with no booster stage, fewer overall compressor stages, and fewer variable stages, shorter high pressure compressor. So you can have a shorter type of engine with higher thrust and efficiency. Higher efficiency as each spool is running at its optimum speed, greater engine rigidity as well as lightweight, and less component resulted to less weight. The main drawback is that they are more complex to build and as well as maintain because there are more components. Example of three-spool engine, as mentioned, Rolls-Royce RB211 in 1972, having a thrust rating of 169 kilonewton. Several subsequent series being developed using this FedEx Full Authority Digital Engine or electronics control, and white cot fan, which increases efficiency, reduce noise, and gives added protection against foreign object damage. And then they are also Rolls-Royce developed Rolls-Royce Trend, and we have the new family of Trend 1000 that are being used in 787 Dreamliner aircraft and the A380, as well as the A350 type of aircraft. So you can have it features the white quad fan and single crystal high pressure turbine blades. This is a modern type of high pressure turbine with improved performance as well as durability. And the core turbo machinery is brand new, giving better performance, noise, and reduced pollution levels. So looking at the analysis of forward fan unmixed 3-spool engine, the layout of this engine and the TS diagram is shown in figure 624 and 625. The air bleed is also extracted from the high pressure compressor at station 4B, which is not shown in the diagram. And using the energy balance for the first full spool, fan and low pressure turbine, you can get expression 669. And when you do energy balance for the intermediate spool, IPC and IPT, you get expression 670 over here. And going through the high pressure turbine and high pressure compressor energy balance, you can then get the expression 670, 71. So this is the layout of a 3-spool engine. So it is more complicated, and this is unmixed. So there's a cold air which is flowing through here, and then the hot air going through this separate pathway. And of course, the more complex TS diagram, okay, for the 3-spool engine. Okay, in summary, so we have already gone through for 3 weeks with regard to this topic. As you can see that I try to avoid in terms of giving example, because once I give example in this notes, I realize that it will need more time to explain. So that's why I believe Dr. An will provide you with, during the tutorial session, with regards to example on the calculation of the thrust for the turbojet as well as the turbofan engine. So this chapter number 6, focus on turbine-based cycle, right? And 2 major types of engines are already analyzed, namely the turbojet and turbofan engine. We also look at a simple application of to both airliners and missile, distilled the classifications and thermodynamic as well as the performance analysis are discussed. Except for the examples, as I said, it is much more suitable to do it in a tutorial session. So next week, we will go into chapter number 7, which looks into the another interesting topic. Okay, so with that, thank you for your attention, and I already uploaded a few set of YouTube videos, and if you have any questions specific to the respective videos that I have shared, you can always communicate or give comments in the chat box in the YouTube channel, and I can always communicate back the answer to you. You can give comments, you can give questions, and we will I'll try to respond in due time to your question. All right, so thank you again, and I'll see you next week on Monday. Bye bye.